as you may see some faces here in the title slide, this is not just my work, although I'm the one who is presenting today. This is a joint effort between our research group and two other professors, Anya and Andre, respectively from Canada and Portugal. And so I'm happy also to share this research with you. And I'm Luca, and this is a curated inventory of programming language misconceptions. I want to start with a brief example, and I'll use Java since it's probably a programming language that most of you know. Now, this is a very simple class, student, that has two instance variables, and we have a constructor that sets those two variables. And hidden, there are some other methods. Now, one example usage of this class in a main class is to instantiate two objects of this class. We store two references and two local variables, S1 and S2. And in this case, we're instantiating new two objects with the constructor by passing in my first name and my last name as the two arguments. And then we may ask a student to complete the following programming task. They should write a condition here for the if statement to print, to check whether the two objects refer to the same student, and in that case, print a line. Now, as you probably may fear, many students solve this task by writing S1 equal S2. And we all know that this doesn't work properly, but still, we might ask ourselves, why does this happen? And why does this happen so often, even though we place some effort in preventing this? In general, we ask ourselves, why is programming so hard? And back in a talk a couple of months ago, Professor Hauswirth already introduced the SI audience to the rainfall problem, which is a famous problem in literature that also you had to solve, and that was also presented to some students at top universities in the last decades, and that presented some surprising results, where students performed really poorly on a fairly simple task. And in Professor Hauswirth's talk, we discussed some of the reasons why is programming so hard. And we identified two prerequisites. The first one is the ability to abstract. So you need to be able to reason about programs. And the second one is knowledge. You need to know something in order to be able to program. Namely, you probably need to know at least a programming language to code your solution and transform your idea into a practical executable program. Now, we'll focus on this talk on the second aspect, which is knowledge. Many research papers try to describe what is the knowledge that is required from programming, and there are many different opinions on this. We took our own from standard literature review by Kian and Lehman, and we refined it to divide the knowledge required for programming into two main categories. The first one is conceptual knowledge. That is, you need to acquire the syntax and the semantics of a programming language in order to be able to program a solution. But just knowing the syntax and the semantics is, of course, not enough to be able to program, because you also need some strategic knowledge, because what you have at the beginning is just an idea and an algorithm. You need to transform it into code. And maybe your initial attempt is not enough because you have to debug your program and test your program. And these are all abilities and skills that fall into the pragmatics umbrella term. I keep using this word knowledge, and I wanted you to give just a brief introduction on it, although I'm not probably the best qualified person to give a whole talk about what is knowledge. I just wanted to give you one of the perspectives that are more relevant and popular in theory. This one in particular is known as knowledge as elements, which is mostly inspired by the work of Di Sessa, who presented his knowledge in pieces theory back into 1993. And he was working on physics education. And he came up with this idea that maybe knowledge is not really this very complex network, but it's a complex network that is made up of very small pieces that are represented here as puzzle pieces, and they are the knowledge elements. And then you need to combine those elements together. You need to form a network in order to be able to solve tasks that are more complex. Now, one key point that research has identified is that whenever we solve a new task, we are never a blank slate. We always bring some sort of prior knowledge for solving that task. And for some tasks, maybe we don't have the right conception to solve them. And so there is what we call a missing conception, represented here by the missing piece of the puzzle. On the other hand of the spectrum, we have a correct conception. So you have normative mental models about how the system works, and you have all the required skills properly connected to solve a task. And in between, there is the problem when you have a wrong conception. So you have one piece of the puzzle that does not fit with all the others. And this is, of course, problematic. And what we want to do in teaching, ideally, is that we want to go from a misconception, which is what friends call the wrong conceptions, to a correct conception. So we want to have the right piece of the puzzle and to connect it together with the others. And this process is called conceptual change. Now, if we go back from the general ideas of knowledge back to the programming misconceptions, of course, there are works on this, but the problem is that we don't really have a neat and clear definition for what a programming misconception is. I'm here showing 3 of the main definitions that can be found in the literature, and let's read them together. The first one is student conceptions that produce a systematic patterns of errors. The second one by Sorva is misconceptions are understandings that are deficient or inadequate for many practical programming contexts. And the last one from the review that I showed you earlier is misconceptions are errors in conceptual understanding. Now, if you look at those definitions, you will probably see that there is not a clear cut between what is actually a programming misconception and what is not. And indeed, people, based on their definitions, have come up with their own lists of misconceptions. These are 2 the most popular ones. The first one is from Sorva's doctoral dissertation, 2012, and it's probably the biggest list with references to the literature that contains and describes all known programming misconceptions. And the one presented on the right comes from a website, csteachingtips.org, by Colleen Lewis, that also lists some content misconceptions she has identified in her teaching practice. Now, the problem, based on the prior definitions, is that these lists are not coherent enough. And also the author themselves recognize this. And this is a quote from Sorva himself that writes that this is a list of not only apples and oranges, but also of tomatoes and the old dried plum. Now, what we can do for this? Well, we thought that if we narrow our scope and we just focus on one of the 2 sides of the knowledge required for programming, namely on the conceptual knowledge part, that is the one that is really tied to the syntax and the semantics of programming languages, we could see an opportunity for a more focused definition. And here is what we came up with. We came up with a new term, which is programming language misconception. And we defined a programming language misconception as a statement that can be disproved by reasoning entirely based on the syntax and or the semantics of a programming language. And I want to emphasize 2 aspects of this definition. The first one is that we really require that a misconception is formulated as a falsifiable statement. The second one being that our misconceptions are really about programming languages. They are not about general ideas in programming. And by general ideas, I want you to give two very small examples taken from the list by Sorva, which I showed you earlier. This is one of them. A set such as a team cannot be a class. Now, this is a misconception that has something to do with the design aspect of our object-oriented program, but it's not really specific to programming languages. The other one is difficulties understanding the empty constructor. Now, this statement describes a general difficulty, but if you think of it, we cannot really disprove this statement. This is not a falsifiable statement. This is just a description of a general difficulty that students have. We want really to formulate our programming language misconceptions as falsifiable statements. And for this, we came up with progmiscon.org, which is a live website that lists our programming language misconceptions, and it describes them in a nice form. And I'm now going to show you briefly what I mean with that. This is an example of a programming language misconception. Equality operator compares object values. That goes back to the example we saw at the very beginning of this talk. This really describes the problem that students have when they use the equality operator to compare the object's values. Now, in this page, we see a couple of interesting features we thought that were important to describe a programming language misconception. The top bar shows a memorable name. This is inspired by the design patterns we have in the software engineering community. We have the main statement, which is the falsifiable statement I was referring to before. And this is the statement that can be disproved by reasoning based on the syntax or the semantics of a programming language. In this case, O equals P compares the objects referred to by variables O and P. Then we have two different modalities of showing what is incorrect on the left versus what is correct on the right. And we show it in a picture, so graphically, and in text with the red and the green boxes. Now, this is an idea taken from the learning sciences, specifically the reputation text, that tells us that it's better to show and juxtapose the incorrect and correct conception rather than just showing the correct one. And then we have a lengthy description of what's really right, and this is the correction section that here is just shown briefly. On the right-hand side, we have other very specific and important elements. The first one being the authoritative source for truth. We really ground our programming language misconceptions in the authoritative specification of the programming language they refer to. For example, this one points to the Java language specification version 13 and to a specific section of it that talks about equality operators. We also tag our misconceptions with concepts that are grounded in PL theory. You see 6 of them here. And by tagging misconceptions with concepts, we allow users to navigate our large set of misconceptions that currently covers more than 200 of them in this very convenient and interactive map in which there is an edge between two concepts when there is at least one misconception that covers both of them. And so here, concepts serve also as a way to navigate our inventory of misconceptions. We say when misconceptions can be covered by notional machines, meaning representations and pedagogic devices that can be used in teaching some programming concepts. For example, here is an example of a stack and deep diagram, which is one of the notional machines we use in programming fundamentals too. And it can help uncover some of those programming language misconceptions. Another way to navigate our inventory is to use the related misconceptions. Now, misconceptions do not often appear just in isolation, but they are very tightly related, and there are different kinds of relationships between them. And here is an attempt that we try to do to capture those relationships and to allow users to navigate them. And finally, we have the same misconception in other programming languages, which is often the case. And we currently cover Java, JavaScript, and Python in our inventory with the goal of expanding to more programming languages. We also have some really neat descriptions that can really help instructors during their teaching. The first one is the origin. We try to tag whenever possible and describe where could the misconception come from. For example, here, students might be used to use the equal operator to compare primitive values, and they might transfer that knowledge to more complex data structure and objects, but that knowledge does not really transfer. We describe symptoms, so things that students that hold this misconception can do. For example, they never implement an equals method, or they use indeed the equal operator to compare the object's state. And talking about symptoms, we also have different modalities of showing symptoms. Here's another misconception from JavaScript. The fact that a constant reference implies the immutability of the object that is referred to by the constant variable. And we have some videos that are watchable on YouTube that show some students that were captured in a research study while solving some programming exercises and exhibiting those misconceptions. Here is yet another one. Parentheses only needed when there are arguments in Java. And we try to use this misconception also as valuable resources. And there is indeed a significant value in many of them, even though when they look very superficial as this one, you might say, well, the forgetting the parentheses is very superficial, but this could provide an opportunity to discuss functions as first-class citizens, which is an advanced topic that is not commonly covered in introductory programming courses, but could indeed be very valuable for instructors. Finally, for computer science education practitioners, we list the references to the literature. So previous published work that refers this misconception. We went through the literature and through a significant body to understand what other people were reporting about misconceptions. And we found that those characteristics were reported in a relatively sparse manner. So we really felt that our inventory could serve as a hub for centralizing information about those programming languages misconceptions and inspire the community to go beyond what was priorly documented. So indeed, we are really building progmiscon.org for professors, teachers, and even TAs to try to help them induce conceptual change and go from a wrong conception to a correct conception. And also, we want to be a hub for computer science education researchers. And this is what I wanted you to show. And I can invite you to go on the website, browse it, and tell us what you think on it. Thanks.